So here, very good. Here you would have Q alpha, the QED coupling times logs of the electron mass, which is kind of the high energy scale, and then the scale of the soft radiation. And now we can resum these to all orders. We can systematically add corrections. So this hard amplitude, we could do to 5 loops. We can also do the soft matrix element to 5 loops if you want. This is something Heribert mentioned. These Wilson line matrix elements in QED are extremely simple. You compute the 1 loop and you exponentiate it and you get the full result.
This is simply because it's a billion.
Yes. So if you draw the diagrams, and it's a fun exercise, if you take 2 Wilson lines, you compute the 2 loop diagrams. There's the regular diagram like this. And then there's the correction cross diagram like this. If you add the 2 up, then by some iconal identities or partial fractioning, you just get 1/2 the 1 loop squared, and this continues. So you just get an exponent. So it's the one case where you can do an infinite order loop computation, basically for free. This type of factorization formula is actually used. So the people who first derived it were Jenny, Frauci, and Sura, and it's the basis for Monte Carlo treatments of soft photons. So these properties are really used. And if you have parton showers, which include photon corrections, then you make use of exactly this type of properties.
Can I ask 2 questions?
Yes.
So one is, I think it's end of chapter 6 of Peskin. He does sort of all order soft photons, and I imagine that maps onto what you've done here.
Yes, but he's not. His computation is not nearly as elegant as our type. Hopefully, you're not publishing these videos. No, he actually finds he does the computation also 1 line at a time, the same we did yesterday. And then he also, of course, gets these iconals, and then he actually shows that this builds up an exponential. So this is in Peskin as well.
And then the second question is, as soon as you say factorization, my ears prick up, and I think of sort of Collins-like factorization theorem.
Yeah, it's exactly the same type of factorization theorem. And it's the same techniques in QCD that you can also apply. So it's exactly the same type of story. The Jenny Frauci Sura way was also very diagrammatical. So you study these diagrams, you discuss this and that, and then you find this result. While we did it in this effective field theory way, which, however, also was closely tied to diagrams. We expanded diagrams, and then I simply asked, well, what Lagrangian can you write down that generates exactly this type of expanded diagrams? And then this was this Lagrangian with this projector and with this V dot D coupling, and then we went from there. And then what was nice is that we got these Wilson lines from this decoupling transformation.
So I don't know if I have a crisp question, but I would, if you don't mind, like to push on this a little bit further. So it's sort of the Collins style factorization. It's about the separation of scales. I think the large energy in a, say, a deep inelastic scattering problem, and then any other scale in the problem, lambda QCD, which is more or less the transverse components and the objects that are sitting inside of a photon. And as far as I understand it, the factorization theorems that I'm thinking of, you're getting the leading order in, say, this 1/large energy.
Of course, it's also here. I mean, we use the leading power Lagrangian, and there would be infinitely more terms. Some of them we have derived. So in the Euler-Heisenberg thing, there's, for example, a subleading interaction between 4 photons. That comes in the full theory from this. It's suppressed by 1/m electron to the 4th power. So this simple formula, this is only true up to terms which are suppressed by the soft energy over the electron mass. So if the energy becomes as large as the electron mass, this breaks down. And of course, all the implementation of this that are used in these parton showers work in a region where it's not even valid. But well, or at least most of them, because they go beyond the electron mass, and then actually this simple factorization is not no longer enough.
But it seems like your method is maybe, I'll put the words in your mouth so that I get the problem when it's uploaded to YouTube. But this seems more powerful than the Collins type factorization, where my understanding is that, going to higher twists is perhaps not fully under control, whereas this seems far more systematic.
Yes, I think for going to higher twist, especially, I think this should be more powerful, and people are trying to do this. And then the thing is, you get many operators. So in a purely diagrammatical way, I think it becomes very complicated. Even, let's say you would do this PDK that we did, where there were two structures. If you try to extract this always from diagrams, in some sense it's possible, but having this operator picture really helps. And it helps because you have sort of a mechanical way of writing down all the structures you have. There's also certain rules like this equation of motion and other things which eliminated them to a minimal set. I think this is really advantageous. Of course, turning it around, when people started doing this effective field theory thing, then Collins Soper, Sturman was quite enthusiastic, but somehow Collins thought, oh, we're just doing the stuff we did 30 years ago. What's the big deal?
There's a little reaction from Collins from denominator regulating.
Oh yes, he was the referee then also. No, but I've had good discussions with him. I think he also has revised this his opinion maybe a little bit. Yeah. But I think especially for power corrections, also if you have several structures that somehow mix into each other, which we'll see in the QCD case, I think this operator picture is again very helpful. And
So this would be like a effective theory for
DIS.
yeah, I mean so that you can just do the standard large x, no small x, large x factorization using these methods. And then of course you get matrix elements, which are the PDFs. You also find that there are several operators you can write down, and the several operators are gluon PDFs, quark PDFs, find that they mix into each other. So you can do these things. However, in this proton-proton case, there's this interesting issue of Glauber phases, which needs an additional Lagrangian. So it's still, the technology is, in some sense, it's now maybe there, but still being refined. So it's not, proton-proton collisions is not yet trivial for this effective field theory.
So then maybe, hopefully the final two questions, I apologize. So who are the sort of the names that are working on these things? So you talked about applying these effective field theory techniques to sort of QCD factorization type processes that I'm thinking of, and that people are working on these techniques. So
there's an entire community. So there's an annual conference on soft collinear effective theory where about 50 people participating. So there is a community of people doing resumations and factorizations in these techniques.
Okay, so the whole sketch people, all right, fair enough. And then the Collins makes this huge deal about Liddy-Sturman analysis and figuring out where the pinch singular surfaces are, where the leading contributions are. It seems like this effective field theory completely avoids that analysis.
No, so this brings us now to today's topic. Great. So the 1 weak point of our analysis from yesterday is I took some 3-level diagrams and I expanded them, and then we wrote this Lagrangian. Once you're happy and once you have the Lagrangian, then you can say, well, now you can do these all order statements. But that I simply can expand is a bit delicate because there are loop diagrams in QED, and should I pin something? Let's see, just so that I see what I'm doing. So this was the stuff we did yesterday with the factorization, and we should discuss loop diagrams and what it means to do this type of expansion for loop diagrams. And this is where different momentum regions and all this stuff comes in. And so the sort of the mathematical basis for this called the method of regions. And it's just a question, how is this thing we did, this expansion yesterday, also valid at the loop level? So again, let me consider one leg. And then I'll do the simplest example. I'll have a loop diagram, always drawing gluons. I have a loop like this, and then an emission like this. Yep.
People online are against seeing it backwards.
Ah, they're seeing it backwards. Okay.
It shouldn't matter.
For the recording or method, but for the people live.
Ah, for the people live, it's a
You are.
yes, but let me. So let's.
I see it correctly. I see it right.
Always.
For me, it's the right way around, unless I'm misunderstanding the issue.
No, me too. I see things fine.
Good. Now you see it. No, it's good. So the question is, so how about these loop diagrams here? Let's say I have a momentum K flowing through here. And then I have, well, actually, let me put K plus Q here. Let me turn the arrow, sorry, and then here I'll have MV minus K. So the Q comes here, goes through this line, and then exits here. And the K is running around the and yesterday we simply expanded, and now the question is, there is this loop momentum, what do we do about it? And it's the only delicate part of this expansion is that these loop integrals, they're not analytical functions. They have all these branch cuts, etc. They depend, you get logarithms of the masses. So these are non-analytic functions, meaning a simple expansion is not good enough for this. So now this is the problem we're going to study. The things that generate these non-analyticities are the denominators in the loop integrals. So we'll forget the numerators for our discussions. So I'll have this integral here. I'll have one propagator for the photon. So this is K plus Q squared. And then I have my second propagator denominator. This is from the electron minus K squared. And I'm now back to full QED without any approximations. And now exactly the question is, can you expand here? What happens if you and it's also immediately kind of obvious what the problem is. This loop momentum, this runs from minus infinity to infinity. So there is a region in this integral where this is as small as this external momentum. This here is soft. So Q mu here is scales like this soft energy is zero. But then the question is, what do I do with the loop momentum? And now what we'll do is to simply go ahead and expand, and then we'll ask for permission later is the idea. So I will now pretend that this K mu is small as the Q. So I say, well, the K mu is as small as the Q mu, and this is this small soft energy. And this is much, much smaller than the electron mass. And now I'll expand. Since I'm a bit bold, I should maybe no longer call this I after the expansion, because it will no longer be true that it is equal to I. The first denominator, there is nothing to be expanded. K plus Q, both counters of the same order. So the integral over K plus Q squared. then in the second denominator, this is actually exactly the expansion we did yesterday. So it's mv squared minus m squared cancels out. Then there's 2 mv dot k minus 2 mv dot k. And then there's a k squared, but k squared is smaller than k. So this is the propagator. It's exactly the Eichel propagator which gave us this. And then there's, of course, an entire geometric series. So it's gone. And then, so it's this minus blah blah plus k squared over 2n dot k plus. So it's an infinite series of such integrals that I get when I naively expand. These integrals, the higher order terms, they have k squared over v dot k. Then they have k to the fourth over v dot k to the squared. So these integrals become super divergent when I do this expansion. And this is because I've kind of neglected that this becomes very large. So I've just expanded pretending that it's a small energy while it's not true. And the price is that then I get very divergent integrals. But they're all regularized in DIMREG. So at least they exist. I can compute all of these. This is not only quadratic divergences, but as divergent as you can get. Of course, now we have to apologize. This is not identical to this integral. So let's look at the reminder. So now I'll call this soft. I'll call the other one maybe high energy. And the high energy part I'll just define as the difference between the full integral minus its soft expansion.
So the reason why you choose to call it high versus hard.
Let's call it hard. Much better. Yeah. I think the reason I called it high was because I called this nodes. Then I changed inadvertently. Well, of course, I can write down what the difference is. dk 1 over k squared plus k plus q squared. And now I can have a very big bracket, which is just the difference between the full propagator minus this entire series of things, minus 1 over 2 mv dot k, and then this entire series of 1 plus. So this is this part.
Do you have the minuses right?
No. Minus plus. Good, so this is this difference. And now the nice thing about this difference, this here, this second part is exactly the low energy expansion of this. So this integral, if you go to very small k, this curly bracket vanishes by definition because the second part is just the expansion of the first. So this vanishes for very small k. So this this integral has only support for k much larger than this, much larger than the q mu than the small scale. So this integral is actually better because this integral really only has support at high energies. And so now, since it only has support at high energies, I will expand this integral around the high energy limit.
So you're only taking the leading term of the soft piece here?
No,
or-
I take as many as I need to take.
But you stop at some order.
I would, yes, I would stop at some order. If, let's say we agree, we compute to second order.
Mhm.
So then I would stop at second order, but then I would say up to second order, this difference doesn't have any support and low energy. And now I can expand this around the high energy limit. And I should only go up to the order where I've done this subtraction here of I hard. Okay, now I'm assuming the K to be much larger than the small energy. So the K is now of the order of the electron mass. And it will now take about 3 or 4 minutes, and then will become uncomfortable. But let's go ahead. So the I hard is integral dk. In this bracket here, I have k plus q. Q is now very small. So this first term becomes a 1 over k squared, and then a long series. All these terms in this series, I'm too weak to write them, but it's again a geometric series. All of them have 1 over k squared, so it's 1 over k squared plus something in the numerator over k squared. So k, 1 over k squared, 1 over k to the fourth, and it continues like this. And then there's the big bracket here, the big curly bracket. In the big curly bracket, there's nothing to be expanded. So the K is large, the MV is large. Here is already everything expanded. So this curly bracket stays as it is. So now the moment of maybe uncomfortableness as well. One thing you notice now that I've expanded this first propagator, I have a 1 over k squared, 1 over k to the fourth. Now you start getting infrared singularities in this integrand. But sometimes it's not that bad, because this curly bracket, this exactly goes to 0. So it actually takes care of this region. There's nothing really happening, despite the fact that it looks bad. So now the moment of uncomfortableness is look at the yellow part of this integral here, this subtraction that I did, and put this together with these integrals here. These type of integrals, the yellow part of the curly bracket, the subtractions times this, they have the form k squared to the minus some power alpha. Then there's v dot k to the minus some power. And that's still more. There are from here which I didn't write. So the lowest order here, there's q dot k. There's also q dot k to the power gamma. So if you compute to the nth order, it's always integrals like this. So what do we know about integrals like this?
0, right?
0, yes, fantastic. So this is just 0. So I've subtracted these things to make you comfortable. The low energies, this exactly subtracts the low energy limit, therefore I'm allowed to expand. But if you compute these things in Dirac, they're all 0. So you might as well have forgotten about the yellow terms. Yes.
Seems like there are still some scales inside them, or you just think it's is small now, doesn't scale.
Yes, but let's look at this. So which scale would you like to look at? The Q. Do an alpha. Q goes to alpha Q. So not alpha. Q goes to lambda Q. And then since this is the prefactor, lambda comes out of the integral, and you get the same integral back. So this integral is lambda times this, and you can do it for the other scales as well. So you cannot get anything non-trivial.
Kind of that scaleless integral versus scale that kind of it's a scale integral with a scale that has k squared plus m squared.
Yeah, there needs to be.
Gives you a scale. Now it's the Q is just a prefactor which you can pull out because the integral is linear.
Yeah, so it's again this somehow things which kind of analytically depend on momenta. So this is all set to 0. You need some non-analytic dependence for a non-zero integral in Dirac. So here the k plus q, there's actually a pinch, and there's really something happens, and you cannot get rid of this. But if you just have products like this, this is not good enough. So since it can only sort of depend on cutoffs if you want, and lambdas, it's regularized to 0. So we set them to 0. So this is the moment of uncomfortableness, maybe. And then, since the yellow part of this bracket is all 0, the only thing that survives is the first term. So this is the original propagate. K squared minus. And so now we have a very simple result. We have shown that the original integral I is the sum of 2 terms. One you obtain by expanding around the low energy limit by treating all the loop momenta as small. The other one you expand by getting the loop, treating the loop momentum as hard and expanding all the soft momentum away. So you combine 2 expansions. First you expand in one way, you compute, then you expand in another way, you compute, you add up the result, and I've kind of proven this here, you get back the original, the expansion of the original integral. And hearing this the first time makes one a little bit uncomfortable, that you say, how can it be that you expand the integrand twice? Isn't there a double counting or anything? And we've subtracted the double counting, and the double counting is scaleless integrals. So the overlap between these 2 regions is scaleless integrals. And
that somehow crucially depended on the fact that we expanded also the k plus q squared in order to be able to argue away these scales.
yes, yeah, exactly.
They will not vanish if you somehow
Yeah.
the k plus q
The
squared.
thing is, what happens in these expansions is the expansions kill certain parts of the integral. So if you look at this integral here, it's really, these integrals only depend on the heavy mass. So they go like the heavy scale, electron, some power, and now of course, so it's d minus 4. D half minus d half minus 2. D minus 4 half. Yeah. So it's 4 powers in the denominator, I can do dimensional analysis. So this goes like the electron mass to the power epsilon. Power epsilon. So it's non-analytic in the hard scale. This is also typically something which goes into the Wilson coefficient. The Wilson coefficient this divergence is 1 over epsilon times electron mass. This is exactly the contribution for the Wilson coefficient. While the other part of the integral this has only the low scale here. The dependence on V is again simple. Since the V kind of factors out, you can rescale the V by alpha. So this has to go like 1 over V times something. And the only something that remains is a v dot q. So it sort of analytically depends on this. And then the rest must be a function of q squared. Now we can again try to count. I've taken away one of the dimensions here. So this is now d minus 2. So the low energy integral on the universe.
1 over m.
Oh, yeah, there's also the 1 over m, of course, yeah. So it then depends analytically on the electron mass, and somehow somewhat consistent in writing. These are not analytically, but non-analytically on the low energy physics. And so this is a typical low energy physics contribution, has a non-trivial dependence on this q squared, etc. Now, this method that I sketched here at 1 loop, the same is true at 3 loops or 4 loops. So you take all the loop integrations, but 4 loops, you have 4 loop momenta. Each of them can be hard or soft. You expand each of them around 2 limits. You get many different terms where some subloop is hard or soft, etc. But you see that for the construction of the effective theory, for the low energy effective theory, you can really simply expand here and you will get exactly the diagrams from the low energy effective theory. For the high energy part, this goes into the Wilson coefficient, and this you get by expanding in the small momenta. So if you really would want to do the matching, you take all the small momenta, you simply Taylor expand all the integrands, you compute, and then you get this scattering amplitude without external momentum. And so this also works beyond the tree level. For this simple case where there are only 2 regions, hard and soft, maybe I wouldn't have needed to do this entire dance. I could have just said, well, we do the soft expansion. Of course, it's not correct at high energies, but we will correct for it by putting Wilson coefficients. So this is what people usually say in effective theory. But since we somehow constructed the entire thing diagrammatically, it's good to have this understanding and to see that the hard part really directly matches onto certain loop integrals and the other one to others. And it's crucial in this construction of more complicated effective field theories like the soft collinear effective theory. I'm only doing soft effective theory in my lecture. But if you have soft and collinear, then the game gets a bit more complicated because you now have a hard region, a collinear region, and a soft region. And the point is you can again get this result by expanding around the different limits. Unfortunately, now I'm at the Fermi lab. So I will not construct the full soft collinear effective theory here, but the starting point is to identify the different momentum regions and then expand. So let me share this briefly on Zoom. So this is was an actual computation of a triangle diagram. I should show you the diagram. This was the 1 loop triangle diagram. And now we look at the situation that is in the scattering. One particle very energetic from the left, the other one very energetic from the right. Introduce reference vectors. We split things into components exactly as you did. And then we'll expand the integrand, assuming different scalings for the loop momentum, K. And so then what one has to think about what regions can contribute. One finds the loop momentum can be hard, of course, all components large, or it can scale like the particle that comes from the left, or it can scale like the particle from the right, or all components can be small. This is called soft here. Then you take the loop integral, you do what we did here, expand in all these regions. In each one, course, you get maybe slightly strange loop integrals with some linear propagators because of these reference vectors, but you can compute all of these. And well, okay, here are some tricks how to compute. And let me go to the result, and then you can ask a question. So or should I? So you compute all of these. They all depend on different scales. The hard one depends on q squared, the hard momentum transfer. The collinear ones depends on the invariant mass of the stuff that comes from the left and the right. And then you get the soft one, which depends on this combination. There are divergences everywhere in these integrals. But if you add everything up, you get a finite result, and it's actually really the correct expansion of this triangle in this limit, which now contains all these logarithms that are fizzled apart into different contributions. So if I would do this construction of the soft collinear effective theory, and I did it in the book, this one starts with this triangle, fizzles it apart, identifies, this is now a la Collins, identifies all the momentum regions and how they scale. And then one would do exactly the same as we did for soft effective theory. We would expand the Feynman diagrams and then ask ourselves, what kind of Lagrangian can we write down that directly produces the expanded diagrams? So we have the Feynman rules and we have to find the Lagrangian. And if you do this, then you get the soft collinear effective. You had a question.
I just want to go back to the scalings that you showed.
So there was a part of this method is to find these different scalings. The statement here is, at least in this one loop example, only these regions contribute. And then there's maybe a little bit of a leap of faith, or you should prove now that also at the two-loop order, only these regions contribute and also beyond.
So basically, what do these? What does lambda?
Lambda here is basically it's the lambda squared is the off-shellness squared divided by q squared, or is the invariant mass squared of the thing that comes from the left and right divided by q squared. So in our case, the lambda, I didn't really use the lambda, but for us, lambda was equal to the soft energy divided by the electron mass. And then all our components of the soft momenta, they go like lambda times the electron mass. The hard momentum, so this is soft. The hard momentum goes like all components scale like the electron. The lambda is even defined somewhere. Yes, so the p squared is a small scale, m squared or whatever you want, the off-shellness, and I write this as lambda squared times q. Good, so the technique is quite useful. So even you can use the same type of technique actually also to, if you ever want to expand some Bessel function around a certain limit where this thing is non-analytic, you take an integral representation and then you insert, let's say you have an integral dx and then some complicated integrand for this Bessel function. Then just insert the factor x to the epsilon into the integrand. Look at the analytic structure of the integrand, find which regions contribute, expand around the different regions, and you'll get the asymptotic expansion of this Bessel function. So it's often a trick, also useful in other contexts. And it's the basis for this field series. Good. So that was the wrap up from yesterday. Maybe you feel uncomfortable, but with this technique, I can basically demonstrate that this effective field theory we constructed also holds at the loop level, and that it was okay to simply expand, because simply expanding gives you exactly the loop diagrams of the effective theory. So the construction was okay beyond the tree level, and this result is really an all-order result. Good. So now we can maybe take a break until 25. And then we'll do jets and logarithms in jets. And this will actually nicely connect to this, what we prepared here for QED. And it will also nicely connect to maths lecture. So we'll get the same equations, or not the same, but equations which can be mapped onto each other.
Right.
Get it on. So now I want to discuss logarithms and their resummation in jet processes. And in terms of effective theory, this is sort of soft effective theory. So it's like that, but without the collinear part, because we haven't really introduced the collinear part. So in some sense, it's simpler than this full sketch, but in another sense, actually, the structure of these logarithms is quite complicated. So it's quite an advanced topic, but it kind of meshes very well with what Matt and Thomas are doing.
This may be a basic question, but does factorization generically refer to the separation of I himself?
It has sort of several meanings. I think the most important is separation of scales. That you take contributions from different scales and you separate them. And this is the case here in the example with the electrons. We've separated the contributions that depend on the electron mass from the ones that only depend on the soft energy scale. So that is the other meaning, is that we've split things into a product. So we have a hard function times a soft function. So it's also factorization in the sense of making into a product. The product is actually too simple already in the, well, we did this example with the two operators. So actually, it's not always a product. It's often hard times soft plus hard times soft. So we had these operators O1 and O2. We separated the high energy physics from the W into the coefficients C1 and C2. And so we again have this, but it's a sum of different products. So that is the meaning of factorization. Sometimes there's a third meaning of factorization. For example, in PDF factorization, people often show that soft physics drops out. And then they use the meaning factorization as things factorize if there's no soft physics. But the term is sort of used in different ways. But from this effective field theory perspective, the important point is to separate physics at different scales. And now we want to do this for jet observables. One could and should say maybe a lot about how a jet cross-section is defined. So we'll do E plus E minus here. And when you do E plus E minus, of course, you cannot simply compute the scattering into hadrons if you want to compute how many pions, etc. This is all deep, it's non-perturbative physics, so this you cannot compute. But what people could compute was the total cross-section. And so for the total cross-section computed in terms of quarks and gluons, you actually get a nice result if you're at high enough energies, which really matches the experimental data beautifully. And I hope you've all seen this very nice plot. It's really impressive. Even a tree-level computation of just E plus E minus to Q bar really nicely follows the experimental data. So all these hadronization effects and that many things happening become irrelevant because it's such an inclusive quantity. All it knows about is the high energy scale of the scattering. Now, the total cross-section is, of course, a good observable, but it's also not very specific. So Sturman and Weinberg were thinking about how to define observables which are more still inclusive enough to be computed perturbatively, but also exclusive enough that it gives information about the scattering at short distances. And so this is what these jet observables do. What Sturm and Weinberg did, and this is kind of the simplest jet definition, is they said introduce some cone from some direction with some opening angle, and then define the cross section as like this. So you take the cone, you wiggle it around until you have as much energy inside the cone as you can have. But then the energy outside the cone, they should be small. So outside the cone, only a small energy should be allowed. And they wrote this as a ratio beta times the center of mass energy Q. So inside the cone, as much energy as possible, outside only very little. And the idea of this is that you can then basically, you will get the anti-quark scattering process plus collections from this. And then you can look at the and I will use this simple jet definition to now discuss these logarithms. It's already clear. So inside this jet, there's a very large energy, basically the center of mass energy up to this small soft radiation outside. So inside we have a lot of energy. Outside we have very little energy. At the lowest order, this cross section is just a QQ bar, but then there are corrections. The reason that you cannot say I have zero energy outside is if you do this, then this will earn in QED. If you forbid radiation, you just get an infinite result. So it has to be sufficiently inclusive. And presumably, if you want to compute the perturbation theory, also the scale Q0 should still be a few GeV, so that everything here is in the let me. This is the jet axis. And now let me just draw a specific configuration. Let's say I have a quark here, and then I have a quark and the gluon on the other side. Something like this.
Not considering software.
And now on top of this, I want to consider emissions that go outside. I will keep this opening angle large. Sturm and Weinberg are particularly interested in a small angle because then you're sort of close to the quark anti-quark and you can fish this out. But then you would also get logarithms of this angle. And for today, one can do this, but I don't want to. So I have a large opening angle. In modern days, this is called a fat jet. The fat jet, two fat jets, and then there's a lot of radiation going outside here. So soft radiation everywhere, but inside there are these hard partons. And now we just discussed this method of region. So now we have to decide what type of momentum regions will contribute in such a process. It's of course soft, so there will be soft momentum. Soft. These are all these yellow things outside. All momentum components are small. They are of the order of beta naught times Q, which is the maximum for the total energy allowed outside. So these they look like beta Q. And then there are, of course, the hard partons inside. So there's also a hard moment region, BH. Of course, it's the sum of all these things which will be add up to Q half or so, but parametrically, these have large energies of order Q. And so now we basically know what the effective theory is. The effective theory is something with hard partons inside, soft being radiated out. And now I can just turn the laptop. We already know this effective theory. It's the same thing we did in QED. We can do the same type of expansions here. So I can take this quark here, expand. I will get exactly the same iconal as I got for the electrons. The only interesting difference, and this will make the structure of logs a lot more interesting than in the QED case, is that you can also have hard gluons. So you can have these hard partons and split here. So you also have to consider the case where you have hard glue. And so I can basically just copy the result from over there. So this type of contribution here, where I have this fixed number of partons at fixed angles, exactly as I had them in the electron-electron scattering. So I will have a hard amplitude. This will depend on all the directions of these partons here. I will again introduce reference vectors. So this will be reference vector N1, N2, N3, N2. The reference vectors are now light-like vectors because these are very energetic massless particles. So the Ni squared equal to 0. So I use light-like reference vectors, and then I will, to set up this expansion, I will expand around this direction. So this depends on this. And of course, it depends on the center of mass energy as well, or on the energy of the energy. So this is this amplitude. E plus E minus here going into 2q bar. Gluon is the thing we look at the moment, but of course we could also take some other configuration. And then I have to decorate this with Wilson lines. Let me write the Wilson lines and then explain a little bit. Difficult to plan here. So one for N1, one for N2. And of course, we have here 3 partons, but we can maybe go up to M partons, and then it looks like this. And then it's the amplitude of E plus E minus to the same partons. So the only difference when we do this iconal is that now this emission here so when you do the expansion with the gluons, the propagated denominators, everything is the same. Of course, instead of the electric charge, you would get the strong coupling, you get polarization vectors, then the reference vector of this particle I here, and then if this is Q here that flows, then it would be N dot Q. So really the same we had over there, but of course there is a color matrix sitting here. So there's a color matrix A if the color of this gluon is A. And I have to distinguish a little bit. There are, of course, energetic quarks. Then the fundamental representation is the one that is relevant. But I can also have an energetic gluon, and it will emit a soft gluon. Then I will get an FABC here, and this FABC, this is just a generator in the joint. So the way, in order not to have to distinguish everything, I will just say, well, it's the generator of particle I. Whatever the particle is, quark, it will be fundamental gluon, it is a joint. And of course, this is a matrix here. And this matrix multiplies the, 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 the color index of the amplitude. So if this is color B here that comes out, then I have color A here in the middle, then there's this matrix here. Here there is, we want alpha and beta, then there would be the alpha here, the beta here. The alpha would dot into this hard amplitude. So here is the amplitude. The amplitude has a color index alpha here at position I, and then this matrix multiplies this color index. Now, unfortunately, when you have m of these color indices, then I would have to write many indices, so people don't like to write indices. So what people do is they use a notation called color space notation, where they write this ket vector. And the ket is just all these color indices, alpha 1, alpha I, alpha m. But these are also pressed, they're implicitly here. And then you multiply this by this color generator A. And since you know it's color generator I, you know that it will act on the index size, but you don't have to explicitly write. Then when I do my Wilson lines, if I now have several of these, they will build up these Wilson lines, or I can do this decoupling. The Wilson lines also are now, they have this color matrix, so I get this SI of NI is a Wilson line along the direction of this. So it is, now I need to pass over the exponential, because this is now really a matrix, and then I have an integral. Here all the particles are outgoing, so I would integrate from 0 to infinity, s, and then I take the color field along the direction, ni dot ai s times ni, the end of the blackboard, times the color matrix TIA contracted with the color index of the blue. So this object here is the usual Wilson line. It goes along the direction of the particle from 0 to infinity. So the collision is at point 0, then all the particles run off to infinity. And while running off, they emit these soft gluons sitting in this Wilson line. And this is proportional to the strong charge, and it involves the generator associated with the ligand. So these are the ingredients. I've written these here without putting indices, but this is now this color space formalism. So this is really an exponential involving this TIA. So this Wilson line S1 will act on the color index of the first part on itself. So this is the factorization. And modulo this complication that there are now matrices, it's exactly the thing we derived yesterday. Just for notation, so this opening angle, let me call this delta or so that it has a name. Of course, this at the moment nothing depends on this, but now I want to write the cross. So to write the cross section, I will take my factorized amplitude and square it and add the phase space constraints. And then also up to now, we've discussed things where all the directions of these partons were fixed. But at the end of the day, when I want the cross section, I will integrate over the directions of everything. If I take the cross section, it will depend on the energy, small energy beta times Q, depends on the angle, and of course it depends on the center of mass energy. It involves these hard amplitudes here, squared, and I'll write them in a second, but if I square them, I get some hard function. This depends on the directions here for the particles, and it depends on the center of mass energy. And then there's the soft function. I will now have to use the calligraphic S. The soft function SM, this is the collection of all these Wilson lines squared. Again, it depends on all the directions. And then, after combining these, I will integrate all the directions. Directions in I, and by squaring, so these color indices here from the soft radiation, they of course they act on the hard partons, so the color of the hard partons change all the time, but then everything is squared, so then the colors at the end of the day are connected. So there's this angle here, this color trace. And then there is a sum. The lowest number of partons I can have is 2. That would be the QQ bar thing. I would have 2 Wilson lines, but I can have QQ bar gluon, so that's 3, and so on and so forth. So there's an infinite number of such operators I can write down. And let me write out the definitions, maybe first of this soft function. This, to get this soft particles, I have to take the matrix element of all these Wilson lines. So I don't have any incoming. Longer. So I start with the vacuum state, then I have my Wilson lines S1 N1 through SM and N. And then this generates a final state XS. This now has soft quartz, gluons, whatever you want. It's still here in this final state. And now I have to square this amplitude. S1 dagger S1 N1. And in terms of indices, so here are these indices which all act on the amplitude and then they connect with each other. Let's say if I have 2 Wilson lines here. These indices, the one here connects to this one, so it's connected like this, but the other end of the index connects into the amplitude and into the conjugate amplitude. So half of the indices are here connected from here to here, while the other half act on the amplitude and on the conjugate amplitude. So it's an object here with 2 M open color indices which acts on the amplitude. And one more thing. I have to integrate over the phase space of all these soft gluons, and I will take a constraint that the total energy of the soft stuff smaller than this beta Q.
Sorry. So the bras and kits, that you draw in here.
No, this exactly to make it extra confusing. These bras here, these are the color bras. So these are new bras which we introduced in order not to write down the color indices. This here is just the regular states in quantum mechanics. So this is the vacuum state, and there are these particles flying around. They emit soft stuff, and the soft stuff is in the final state. So these are the usual Hilbert space states,
Which don't have color indices.
Yeah, there are colors which contract with them.
The soft state, this talks about the gluons in the exponents now of your Wilson lines.
I mean, this yellow here, this thing is just all the yellow stuff that's it here. So here there are all these gluons, and of course, try more drawings.
So I guess then I'll say that the state XS has a color index because that's the color of the soft gluon, but then you're summing over all of these colors.
I mean, these when you do perturbative computations, it will expand these Wilson lines. So this is one at the lowest order, and then there's a single gluon field, and this gluon field generates or annihilates stuff which is here. So there is a color index which gets contracted with this.
It's the gluons that come that sit inside the Wilson.
You are then summed over because you are summed over.
Yes.
So
You mentioned that there were.
So let me do a drawing with one Wilson line. So there is one index which will connect to the amplitude. So this is index I. This is in the amplitude. This is this Wilson line. And now I've ruined my color coding. Now I have to draw gluons. So this can emit a gluon, and it can attach either to this Wilson line or to any other Wilson line in the game. So you would compute this diagram to get the one loop correction to this soft function. Or you would, if you do the two loop correction, you would maybe compute the diagram like this, going to some other Wilson line shape. And Heribert has this two loop computation on his desk.
And XS talks about the blue lines.
The blue lines, the blue is the XS. So this state here is one gluon here. So this is XS, here is one gluon. So here it would be just one gluon. And then there's a loop on the other side. But of course, you could also have two gluons. So we can also have gluon.
And so the XS are final states.
These are the soft parts, the soft final states.
Right.
So in my drawing here, it's 10 gluons. In this drawing here, it's 2 gluons.
I'm guessing you're fighting with the open indices on the Wilson lines.
Yeah.
Yeah, these go into this one. So again, maybe let me write out. It's not writing color indices is of course fantastic if you have to write, but not fantastic if you have to know what it means. So there is the S dagger here. Let's say 1. This has a color index A prime B, and then there's stuff in here. And then there's the S1 here on the other side. This has a color index B and then an A. So this color index B is summed over. This color index A acts on the amplitude. So here is an index, color index A in the amplitude. And then the index A prime acts on the color index, the conjugate amplitude.
the color index P is the index of the produced jet part or the hard part.
Yes, so this is,
And the color is.
So-
I mean,
so-
when it's produced.
yes, so you start with a quark, let's say, with color A. Then this Wilson line comes, it emits 200 gluons. The color gets completely messed up. At the end of the 200 gluons, its color quantum number is B. And so that is sort of what remains at the end, and this is then contracted with the other one.
So if we want to put those XS states in,
These XA states are sort of on top of this. Now I can take a matrix element with these blue gluons and with the yellow ones.
In fact, already in some sense implicitly done that, where you had some polarization vectors with colors.
Yeah, so here, so if I really want to compute something, then I will have to start with states. Let's say I have the vacuum state here. Then you would say, well, I can only have loop corrections or nothing. So all these A's have to take care of themselves. Let's say I have two gluon states. Then each of these Wilson lines, one of them has to do an emission, all the other ones should shut up. So then you get one emission from one of these. Okay. Let me try to draw again. So I have, let's say, two Wilson lines, 1 and 2. These indices here, they will connect to the amplitude that is in here. And then there's the other thing in the conjugate amplitude. And then these indices contract with each other. So that is, if is there a vacuum in here, then this is the contraction of color indices. The color index of the amplitude contracts directly with the conjugate amplitude. But now I can emit a gluon from here. So now there will be this T1, and it has as color indices, and then there's the A here and the A here. Now the colors are contracted like this. And now this yellow thing, this is one gluon, so the state XS is equal to this gluon. And it has, of course, a color, but the color in the amplitude. So in the amplitude, you have a gluon with color A, it's contracted with the color of gluon in the conjugate amplitude. And at the end, so at the end, of course, all the colors are always contracted. This is what I conveniently indicated with these brackets without. Yeah, then I understand that the notation is tricky because I have so many indices and everything contracts into everything. In some sense, I think the drawing is the simplest thing. Yeah, so there's the hard amplitude, M2. It has two legs here. Two legs which connect to the Wilson lines, which makes the soft emissions, changes the color. And then on the other side, there's the dagger of this. And
these two M's together make a hard.
this will make the hard function, which I should write down next.
And now I'm putting again words in your mouth. Why do these the two S's, one from the amplitude and the other one is a dagger, the other isn't. They are aligned the same way, so why don't they cancel? I think this is what you want to ask.
Well,
I think it's because
they're not. They're in a completely different world. How can they? I mean, there's a state here in between. If you would if sum over all the states or something, you would take this out, then all of this would immediately cancel out. But
it's not all, right? I mean, these states are soft only. I think
yes.
that's what makes it. What makes it happen.
Well, I can't sum over. I mean, I impose constraints on these. Their energy has to be smaller than something. I cannot sum over everything. Or if I do, then I have to drop the constraint. Then all of this goes away. And then you're back to the total cross section. The total cross section only has the hard functions, and you get the usual result. But with this constraint, they don't cancel. Good. So now the hard function. Now for the amplitude, we have this color space bracket notation, but I'm not allowed to immediately contract these color indices because all these Wilson lines act on them, they all change. So this hard function here look like this. We will have the amplitude for the m partons along the n directions, and then it has the conjugate amplitude, but squared in this way, so that these color indices are open and these color indices are open. I will then take this soft function and squeeze it in the middle, and then contract all the indices, and then I get the cross section. And I want these soft emissions, they only know about the directions, so I can integrate here over all the energies of these hard partons. So I have an energy integral dE times e to the e minus 1 over some factors of 2 pi squared. I'm taking the usual phase space, but I want to do the energy integrals, but I'm not doing the angular integrals. I'm keeping it everything at fixed angles, and the angular integrals is this symbol here. So some of the 2 pi's will put in the angular integrals, other 2 pi's I get to put the 2 here. So that is this, and then there are of course phase space constraints. So there is the energy momentum conservation. Q minus the total energy of these hard partons. Then if you're in the center of mass frame, there is a delta function that the total momentum has to be 0. That's the definition of this frame. So total momentum of this is 0. And then there's a last constraint. The last constraint says that the partons have to stay inside the jet. They have to, the hard partons are not allowed to go out. So there's a theta function in which depends on these directions. So then all the hard partons have to stay in the jet. So that is the hard function. And writing this, I see that I did a little bit of a mistake here. It's not the total energy that counts, it's only the total energy in this gap. So it's the energy total outside that plays a role. Inside the jet, there's no constraint the emissions can do, but if they go outside, the energy has to be smaller than beta. Good. So this is this factorization theorem, yes?
So I realized that the notation that you've chosen, those amplitudes aren't exactly Browser checks, but you've chosen to write them in a way that looks like an operator.
So this bracket, this is really only in color space. So this is this color space bracket.
But is there any?
This is the C that you had on, like, essentially.
Yeah, exactly. Here is for these C's times spinners.
Yeah.
This gives the amplitude. And of course, in QED, there were no indices, so everything was nice and easy. Here I have to now keep track of all these color indices of everything.
Right, so this.
But other than the color indices, it's really the same. This formula here is the same as this formula. Now I've squared the entire thing. I've taken the matrix element of this soft Wilson lines. This is the soft function, and then this is the one.
Right, so I'm assuming that the function already has Wilson color indices as well.
Yeah, this has exactly, this has I color indices. So if I write this hard function out, it's really the amplitude. So if I would write the indices, this would be m alpha 1, alpha 2 to alpha n. This has m color indices. And the complicated one has n, alpha 1 prime, alpha 2 prime, alpha n prime. Then the indices from the Wilson lines here multiply the alphas here and turn them into betas. The indices on the left here multiply the alpha primes and turn them into betas, and the betas are contracted with each other in here. And in principle, all the color contractions are the same we would do in a regular amplitude. The only painful thing is I have to do this sort of an arbitrary number of things. So there's, yeah. So this is the factorization theorem. And the nice thing here is that again, we factorized the soft function only depends on this q times beta on the small scale. The hard function, as you see from the definition, none of these particles are ever outside. It doesn't know what's happening outside. It only depends on the center of mass energy. So we've completely separated, and so we can use this to resum logs of the ratio of these two scales, so logs of beta. So we can now do resummation. So that was the first half, is the factorization. And now we'll do the resummation. And in principle, this is now again, in some sense it's straightforward. So we have these H's are the Wilson coefficients, and these S's are the low energy matrix element. So it's exactly what we practiced in lecture 3. So we wrote at Wilson coefficients C1 and C2, operators O1 and O2. The only problem here is that we have infinitely many of these. That's a slight complication, but other than this, it's the same as always. We already know the equation dV log mu of the Wilson coefficients. So there will be divergences. So we renormalize these. And then we do dV log mu of these hard functions HM. Write all the arguments. This is the same as the hard function times the anomalous dimension matrix. This is it. This is the Archie evolution equation that we have to solve to resum these logarithms in J processes. And you can immediately write down the solution. It's just a path-ordered exponential of an infinitely large matrix. And it's, of course, we've already said these matrices, they have color indices. So if you have m equals 17, then you have 17 color indices. So you're in the space of the color of 17 partons. And then you also have to sum over all these m's. So that's what makes it a complicated equation. There is one thing that helps a little bit, is that if you're going to a given accuracy, let's say 1 loop, then this matrix simplifies the relatively sparse matrix. We've already drawn some diagrams that you can have at the 1 loop level in this soft function, and all you can do is exchange one soft gluon, and this anomalous dimension would sort of be in the ultraviolet part of this, or maybe easier, the infrared part of these hard functions. So at the 1 loop level, you can either have loop corrections, a 1 loop correction, And so if you start with 2 partons and do a loop, you still have 2 partons. 3 partons the same. Or you can do a real emission where you emit an additional parton. So this R2, but the R2 actually adds 1 parton, so you're in the space of 3 partons. And other than this, there are only zeros in this matrix. So the one loop is not as complicated as it could be in general. And we can rewrite, we can use this and then rewrite this equation. We have a new.
You see that the gamma acts with the left index, so right? So you see that the 3
Exactly. So let me
feeds into the 2.
yeah, let me write. So if let me write the diagonal terms. So alpha s over 4 pi. Then I have HM times VM. So that is half of this. That is this contribution here. If I do the off diagonal one, then I have to start with 1 parton less, and then I get the R and I go back to M. So I can also have plus HM minus 1 times the R minus 1. Start with M minus 1 partons and I add them. So that is this.
Go back to the other report where you have the definition of the hard function A. So nice with this.
No real lines in this. It's just R and so
It's not this redefinition of the fields, but
this somehow we have already done. There's the sit here, yeah. These are now just amplitudes with a fixed number of partons. So the question is, how can you derive this anomalous dimension? What you do is you look at this hard function and then you say, well, I can get these as infrared divergences from this. So let's take the one where I have n plus 1 partons. And let's say that one of these partons now becomes soft.
okay, so that's how you.
And then if one of these partons becomes soft, then I can take out an iconal here and an iconal there. And then I get the product of 2 iconals is then this soft anomalous dimension.
Okay, so okay.
Exactly. And then you get this.
You get this anomalous dimension by taking the 3 level 1 matrix element, then you start calculating.
Exactly. So we can look at the soft limits of this have to match the high energy limit of this. So we can look at soft limits of this. And then that's why this anomalous dimension looks like it comes from soft. It's because the infrared divergences are soft, but there are no Wilson lines in here. And all the partons that I generate are always hard partons. They're all inside. So this form of the equation is already a bit nicer. So if I take this away, then I can basically solve this modulo the color structure. So one simplification that many people then do is to go into the large NC limit. Then this becomes again simple. Then everything becomes numbers, and then you can immediately solve this one, and then plug this back in. So a nice way of writing the equation is to introduce solving or reformulating the solving numerically. So I can introduce something called shower time, and it's just a variable transformation from mu to something else. Last time I went from mu to alpha. Now here to do this alpha is the alpha over beta alpha. This is the d log mu. And then there is an alpha over 4 pi. So if I bring the d log mu to the other side, it's d log mu times alpha over 4 pi. This is exactly this time written in this way. And so then rewriting the equation in this way, we can solve the homogeneous equation. This is just an exponential of this v and plug it back in, and then you get this equation here. That is hm at time t can be obtained as the hm and t0 times an exponential of t minus t0 times the virtual. That is the solution to this equation after rewriting it with the time t, plus integral t0 to t prime h m minus 1 t prime times the rm minus 1 times e to the t minus t prime em. It's the same equation, and in some sense it looks more complicated, but I have explicitly solved the parts associated with the virtual ones, and then for the real ones I get this integral. And the reason for writing it this way is that this is exactly what the people do when they write the parton shower. In the parton shower, there's always a no branch probability, so they will tell you, well, you have m partons, and then these m partons can stay m partons, so there is a no branch probability. Or what could have happened is that at some earlier time you did an emission at t prime and you generated this additional parton. And if you look at this equation, one can solve this iteratively. So at the time 0, the t equals 0 means this is the same as mu equals q. So that means I don't impose any veto on the outside. And so then if the time is 0, there are also no large logs. Wonder whether I should wipe. I hope we don't need it in a second. So at time t equals 0, I can start with the minimal amount of partons, with 2 partons. I could also have 3 partons, but 3 partons have an alpha s. And now since I'm at time t equals 0, there are no large logarithms or anything. So 2 is good enough up to order alpha s corrections. And then I can solve this equation in Monte Carlo way by producing a new time t1 distributed according to this v2. So I come to time equals t1, and then time t equals t1, one can produce an additional emission here. So I started with h2, and now I move to h3. So h2 into h3. Then I do another step, and I can add another parton, and I come to h4. So this is T2. And then you continue this process. And this you can really implement into a code. So it's a code that throws random numbers in T and then produces an emission. And for this emission, you also randomly choose a direction. So what I get if I do all of this, I have an H2 times I have an H3 iteratively. So if I evolve all the way to time, to the final time that I'm interested in, so let's say I have a value of T final, which corresponds to the Q naught that I'm interested in. Then I would run my shower until I reach this time t0. So I would run and then I would get all these times. So at the end, I would have this h2 at some time close to the finishing time, u0. If I do this many times, I always generate h2s, and maybe hopefully at one point I'll get it exactly at the t value that I'm interested in. And I'll also get from iterating here an h3 at the low scale plus all the other h's. And now I have to combine these with the soft functions, but now I'm at the low scale. At the low scale, this soft function, I'm at the low scale, mu naught is equal to q beta. The final. So there are no large logarithms in the soft function, and so I can perturbatively compute the soft functions. And the lowest order is good enough, and at the lowest order, all these Wilson lines is e to the something with a g, so they're all 1. So I have a 1 for this Wilson line, a 1 for this Wilson line, and a 1 for all the other Wilson lines. I have to integrate the directions of these additional partons that I've generated. But actually, this nice parton shower, it generates random directions. So if you run it 1 billion times, then it will sort of sample all the different angles, and so it automatically does this integral. So the shower does both these t's, and it also does these angular integrals, and so then I really get the cross section. I get this cross section and see as a function. And by doing this way, we started with the hard function at t equals 0, didn't have any large logs. We ended at the soft function at mu f, didn't have any large logs. So all the perturbative expansions were well defined. So we did exactly the same that we did in flavor physics. And so again, we resummed all the logarithms using this Archie improved perturbation theory. But the price was, things are quite a bit more complicated. We need to write the computer code. It was only valid in the large NC limit to do it, so it's a bit more restricted. But in principle, we can go to higher orders here. So if I go to one loop order, then I will also have to include the one loop correction here. That's the order alpha S suppressed, but now I'm going there. I also have to include the one emission term, that's also alpha S suppressed, but it's there. And then I have to do the evolution of these. I also have corrections to the anomalous dimension, so I can start with the H2, but then use the 2-loop anomalous dimension, which also generates a correction. And now all of these we've actually implemented, and I've shown yesterday some plot. So we can do this resumation not only at the leading log with the shower, but we even have a shower that produces these subleading logarithms. So this part, as you have noticed, is relatively technical. This is cutting edge research. So these are the things I'm working on at the moment, implementing these corrections, putting everything together. What I like is that we really got a parton shower out of a factorization theorem. So it was really a systematic theoretical statement, and then it translates into a parton shower. While in most lectures I've heard on parton showers, it somehow comes a little bit out of nowhere. They say, well, the particle can branch or it cannot branch. They write some equation, and then they put it in. Well, here it really came out of quantum fields. Good. So you should pat yourself on the back for surviving all the way to the end. So that's it.
Thank you. Thank you very much.
So this reminds me very much of trying to do energy loss calculations in ion collisions, and especially having multiple emissions. And the difficulty there is always the quantum mechanics, if there's quantum mechanical interference. So the fundamental block for us has always been putting it onto a computer code, into a Monte Carlo. You're never able to capture the quantum interference.
This, of course, is also quantum mechanical. So there are amplitudes and conjugates, and there are phases. And people are trying to put these phases and everything into Monte Carlo. So Simon Platzer, Jeff Forshaw, etc. They try to write a parton shower that's not using the large NC limit and puts the full structure. That is one. The other thing which I should have remarked, which I said at the beginning and then forgot at the end. So this complicated set of equations, they map onto what Matt was talking about. So we've already seen, so there's a dipole if you want, and then there's an additional emissions. There are also all of a sudden three, for me it's hard partons, there's 3 hard partons, but the 3 hard partons come with 3 Wilson lines. Then there are 4 hard partons. So this equation is somehow complicated tower of equations. So it's exactly the same as this Jimbock tower. And this was pointed out by Heribert that you can do a strange conformal mapping, which maps the directions here in these integrals. So there, I integrate over the direction. So it's 2 angles, and you can do a stereographic projection and somehow map them into the 2 transverse components that Thomas is working with. So these equations map into each other. So this BK Jimbock can be mapped onto this. And there's even interesting work by Karama, for example, tries to use basically these equations and then compute things on the other side by computing here with soft partons and then mapping it to the other side. It's also something I would like to better understand in the future. In particular, I would like to know if this 2-loop anomalous dimension that we computed now maps onto the 2-loop anomalous dimension on the other side, which
is what we are also interested in. We might be worth talking more about this.
Yeah.
We have more questions. So I have a little, okay. I hope always a little trouble now. So what you did here is one hard emission after the other in the hard part of the square.
Yeah. Because I'm evolving the hard function down. It's only once I'm down at the low scale, we'll start talking about the soft.
Yeah, and then the soft becomes trivial in
Well,
the end there, right?
when we do this next to leading order, we really have to take the one loop matrix element of M Wilson lines. So when we put the corrections, we also put the corrections to the soft.
So that, okay, that then promotes the soft ones to trivial.
Yeah.
Okay. I think we need to talk about this a little more offline because this gets technical very quickly. We have anything else that you would like to ask Thomas directly? Well then, thank you again for a whole week. Very hard work.
It's great to be here, and I look forward to another vacation weekend. First, do a good recovery with a long sleep on Saturday, but then maybe a trip to the Cape with Thomas.
Very good.